So this is the XC to XE comparison and early performance tips. I'm guessing that maybe not all of you, but at least some of you have been working on ROSA. So I'm going to compare and contrast, and I have a processor bake-off kind of that we'll step through. Pretty dense slide, but hopefully you also it'll be a good slide to reference, and you can tell when you are running a different speed and why. So the basic outline, only these are the topics that we have to do. So the node is similar but different. You'll see what I mean there. You have the choice of hyper-threading. Like I said, Intel was a little surprised yesterday when they, or a couple days ago when I asked them, well, what are you going to say about hyper-threading? And they're like, oh, HPC doesn't use hyper-threading. Well, guess what? Now they do. So core specialization, it has been around, continues to be around, but there are twists to this. So we're going to go over that. Software environment is similar but different. I'm going to point out a couple of MPI enhancements already now, because most of MPI is similar, but there are some that are couple that are new and important, I think, to this environment. So we're going to touch that here. Hyper-threading. Then we're going to take that and develop a hyper-threading optimization chart. Talk a little bit more about Intel OpenMP, network sustained bandwidth, brush up on your I/O, and then if we have time, I even have a 3D FFT story that was something that we did, learned on the XE, but probably is still applicable. So we'll see how far we get through all of this. So first thing, this is an Interlagos compute node. Interlagos is AMD, this is ROSA, right? But I wanted to refamiliarize yourself with that, so then we're going to move forward. The things to remember about Interlagos is that you had a connection to the internet through their HT link. All right, the fact that it's HT isn't so important, as there was one connection connecting into a single die. A single die of a single socket. The node was 2 sockets. Each socket had direct attached memory, but inside those sockets, each had 2 unique die. So from a programmer's point of view, really, I would say that this wasn't a 2-socket. Don't think of it as a 2-socket system. Think of it as a 4-die node with an interconnect between those 4 die. At a high level, we'll see this is relatively similar to the XC compute blade with Intel inside. We have 2 sockets. Each has direct connections to memory, and there is one of the sockets attached to the network. So in that sense, they're similar, right? Both have 2 sockets. Both have one of the sockets attached to the network. Both of the sockets have direct attached memory. The thing that's different is on Intel now, instead of having 2 die internally, we really have 1 monolithic die. So before, we had each die had a total of 4 bulldozer units. And each bulldozer unit, they had their own interesting definition of what was a compute CPU and what was a compute module and stuff like that. But they had 4 bulldozer units for a total of 8 threads on here. Here we have 8 cores in this socket. And each core is capable of having running 1 or 2 hyperthreads. So we're not going to, if we're thinking about shared memory programming, on ROSA, I would have recommended don't go beyond a die, and a die was 4 bulldozer units, right? 4 bulldozer modules. Again, I would probably recommend for OpenMP or shared memory programming on the Cascade, don't go beyond a die, but the die is now 8 cores total, each with hyperthreads, or not. So similar, but a little bit different. Now we're going to go into a pretty dense slide, but we'll step through this little by little. And I made it dense. I wanted everything on one slide for a reason, you know, and you'll get PDF versions or already have PDF versions of this, and you'll be able to reference it a little bit. So on the left-hand side, we have Interlagos. On the right-hand side, we have Sandybridge. And we'll just walk down each bullet point. So on the left-hand side, Interlagos had 8 core modules, is the term that we came up with, per socket. But those core modules were split between and had 4 core modules per die. Right-hand side, Sandybridge, 8 cores per die. And there's only 1 die per socket, right? Next one, 4 die per node, because we have 2 sockets, 2 dies per socket. On Interlagos, only 2 die per node. Again, this is repeating what I just said. Fewer die means fewer NUMA nodes is a term that people use fairly often as well. Core, yeah, so we've had Cray over the last almost decade has had real problems with terminology. And that's because everyone a decade ago knew a CPU was a processor, was a core, was a socket, right? But as we've progressed into the multi-core era, Cray has had to, since we write contracts on this stuff, we've had to try and be precise and add terminology. It worked out pretty well when they started putting multiple cores on a processor, because then we would say, oh, okay, a processor is maybe a socket, and you would have multiple cores in there. It began to break down when they put multiple dies in the socket, and with Interlagos, it really began to break down, because Interlagos, they have, their code name was a bulldozer module, and that bulldozer module actually has 2 integer units, but shares a floating point unit. And people stop really saying, well, what's a core? You know, depending on who you would talk to, they would say, what is a core? What is not a core? And so we came up with the term, well, core module refers to this bulldozer module with 2 unique integer functional units and a shared floating point unit, a shared vector unit. On Sandybridge, you can basically think, well, that's a core, because everyone in the Intel world still calls it a core with 2 hyperthreads. So we're kind of going back to the term core, because that's what everyone wants to talk about in Intel land. So you can think of a core module. If you want to briefly think about Interlagos and then move on, you can think about a core module as being similar to a core on Sandybridge. So let me go to the next line. Like I said, the core module has 2 integer functional units. Each integer functional unit is capable and basically runs its own process thread, right? And the default way of running on Interlagos is to, in fact, pact a 1 process thread, 1 rank on each one of those integer functional units. On Sandybridge, like Intel hinted at two days ago, the default way of doing it in all of HPCC is to run just 1 process thread per core, and that's why everyone calls it a core. But we have the capability of running either 1 or 2 user threads at runtime. So all total, if you multiply everything out, the number of core modules times the number of sockets times the number of functional units, and you say you're going to run 1 process per integer functional unit on Interlagos, this would fit 32 at default. I'm almost certain that's the way it's set up on Rosa, right? And for Sandybridge, if you multiply the number of cores times the default number of threads per core times the number of sockets, you end up with 16. So there on the Sandybridge side, at default, you're going to be running 16 ranks per node with the choice of going to 32. Got it? I'm willing to pause here for a minute because it's the source of quite a bit of confusion sometimes inside of Cray as well. So continuing on, the core module, this bulldozer module on Interlagos, had 2 AVX vector functional units. Each was 128 bits wide. And what they would do is they would take the AVX instruction and actually, under the covers, split it up into 2 128s and then feed it to the vector functional unit. On the other hand, Sandybridge has 1 AVX functional unit, and that is 256 bits wide, and they don't break it up. So on Interlagos, you could still compile SSE vectors that were only 128 bit wide and get potentially pretty good performance. It's less clear that that's the case over on Sandybridge. On Sandybridge, if you're going to vectorize, you might as well go whole hog and vectorize AVX and get the 256. So Sandybridge, in short, is even more AVX. I mean, it's more a pure AVX thing. You strongly recommended to compile with that XAVX when possible. Another difference on the left-hand side, Interlagos had 1 fused multiply add functional unit. So fused multiply add is they have a single instruction that implements both a multiply and an add. If you did more multiplies, or if you only wanted to do a multiply, basically what happened is it filled in the add of a 0 to implement the multiply. If you only wanted to do an add, it filled in multiply by 1. So if you didn't have an even balance of multiplies and adds, and if the compiler couldn't arrange to fit those multiplies and adds and instructions, your peak would actually drop by half. Fortunately, for HPL in the top 500 list, I mean, it's easy to put multiplies and adds together. You have exactly the right amount at exactly the right time. So it worked for HPL, but it was a challenge for compiler writers there. Sandybridge, on the other hand, has 1 adder unit and 1 multiply unit. If you want to do a multiply add, one would do the add, and then a few clocks later, one would do the multiply. If you have 2 independent multiplies, well, they would still only go down the multiply unit. If you had an add that had nothing to do with the multiply, well, 1 add could go on here, 1 multiply could go on there. So in a way, this is a little bit more flexible. Now, of course, they hinted at in future generations, they're going to add the fuse multiply add. So we're going to go back to having a fuse multiply add, but they're going to add in a way that they add it to both units. So again, to double the peak in the future, they're going to go back to fuse multiply add. But a little bit difference in here, probably this is really getting down into the details in terms of peak, but it's an interesting difference. Perhaps the biggest difference is going to be in the cache structures and the speed of those cache structures between the two processors, between the 2 cores. On the left-hand side, we had 2 by L1 cache. So I think the 2 by means each integer functioning unit had a 16K byte data cache associated with it. So you could think that per core module, they had 32K bytes. But really, your process, if you were trying to cache block, your process would have only 16K bytes of data. On the right-hand side, they have 1 L1 cache of 32K bytes. Now, if you were running hyperthreading and 2 threads per core, that would be 16K per hyperthread. But here, it didn't matter if you were running 2 per core module or only 1. You had 16. And this was a source of some performance surprises because there was a few applications that came from another Intel processor or came from Magnicores that no one ever really thought of it, or someone did think of it, and they were getting good L1 cache reuse as long as it was something like 32 or 64 kbytes. And when it dropped down to 16 kbytes, that was getting anemic, and it was dropping out of the L1 cache. So generally speaking, I probably would say I'd rather have this because 32 kbytes, and if you only do one thread per core, that's going to give you a little bit more space. The L2 cache is kind of flipped here. The L2 cache was 2 megabytes, so that was really nice to have a 2 megabyte L2 cache. Over here, it's 256 kbytes. While this seems huge and this seems less, there's probably a couple of mitigating factors why that's not such a huge advantage over here. The first one is if you look at the level 3 cache, this was 8 megabytes on a die. So 8 megabytes on a die, which was 16 megabytes in a socket. But one die could not cache in the other guy's. The bulldozer on one die could not use the cache on the other die. So it was, 8 megabytes is what you had to think about being shared between 4 core modules if you wanted to do cache blocking. Over here, it's 20 megabytes. So it's bigger than even the 16, if you want to think of it that way. And it's uniformly shared. They have a ring in there, but as far as I know, no one can detect that ring structure. So it's uniformly shared across the 8 cores. And again, if you are running in the default mode, you actually have fewer threads using those 20 megabytes. So the fact that the L3 cache is bigger is going to be helpful on the Sandybridge. The L2 cache, getting back to that, so yes, it is smaller, but 256 kbytes, at least that's respectable. It's relatively easy to cache block for that if you know its size. And even if you don't cache block for it, that's still big enough to capture a lot of working sets, the smaller working sets. So if you count this all up and you say the cache per core module over here, each core module had 2 megabytes plus 8 megabytes divided by the 4 core modules. That's a total of 4 megabytes per core module. You can do this addition on the left-hand side because they're what they call exclusive caches. What is in one doesn't have to be in the other, so you can add them. On the Sandybridge, its cache per core is basically 20 divided by 8. And I don't add in the L2 cache because A, it's relatively small, and B, they're not exclusive. Whatever's in an L2 cache has to be in the L3 cache. So total cache per core is going down a little bit, but it's still a respectable 2.5 megabytes. Now we get into a little bit of a wow factor here. So this is the bandwidth per core module, and this is the bandwidth per core for each of the 3 levels. Level 1 on Interlagos is 49 gigabytes a second. This says measured by streams, run it with all cores running simultaneously, even if you are just going to your L1 cache, and so the other ones should be independent. Streams triad, I should say. That's 2 loads in the store. So here's cache bandwidth per core module. L1, 49. L1 over here, 105. So this one, the L1 is slightly bigger, but twice as fast. And I really do think that you can see this on some of your applications and some of our performance. L2, 27. L2 over here, 42. Not quite twice as fast, but 50% faster. Again, a nice performance boost. And then over here for L3, 27 gigabytes, over here 26 gigabytes. So one of the things that has been observed is, you know, this is you have to pick how you want to do the comparison. If you compare at default, you've got 32 guys over here sharing memory bandwidth and cache bandwidth, where the cache bandwidth of the L1 is 49 gigabytes a second. Over here, you've got 16 per node sharing the memory bandwidth, sharing the cache bandwidth, and your cache bandwidth at L1 is 105. If your code is you know, L1 cache friendly, I think there's a lot of things that really get a boost on Sandybridge. If your code is completely memory bandwidth bound, if we look at the stream triad per node number, so this is both sockets running simultaneously but doing streams to their local memory, it's 70 over here, 77 over here. 10% increase, but not a doubling. So if you're moving from Rosa to Sandybridge, Rosa with Interlagos to Daint with Sandybridge, you're completely memory bandwidth bound. You know, don't expect a 2x per node. Expect maybe something on the order of 10%, or maybe with better architectures, more than, you know, with all the other nice features in Sandybridge, maybe more than 10%, but it's not going to be a 2x per node if you compare on a per node basis. Yeah?
So our boss has rather strong feelings about things. And
most bosses do.
Yeah.
You know?
So when I show you benchmarks that aim considerably more of a speed up on our bandwidth limited applications than 10 or 20%, that's very impatient with me. I'm just wondering, is that really what people experience with bandwidth limited applications, is 10 or 20%? Or are there perhaps other reasons, for example, the bandwidth of the cache, for example, which is considerably higher in L1 and L2
Yeah.
than the Interlagos? I mean, what do people really experience with bandwidth?
So the first experience in internal to Cray, and on some of our own marketing material, but also now that I've seen from users, is there's a wow factor going in there, but you have to dig deeper. And the wow factor comes partly because on Magnicores before this and Interlagos now, they were running 24 or 32 ranks per node. And when they just jump on Sandybridge and Daint, they're gonna default is 16. So when they take a per rank number and compare it, they all of a sudden, they're not seeing 10%. They're often seeing 2x or 3x. And that's coming from better cache behavior, slight improved memory, but they also have to be careful that they're actually running fewer ranks per node. I think if you do that node to node comparison, it's closer than the 2 to 3x that people often say. You know, I don't know if I have an exact number. Like I said, I think you will see, it will be very common to see more than 10%, because this cache structure, that architecture does seem to be better over here. So that's, I think there's a lot of things that are going for Sandybridge besides this 10% improvement. But this is to make sure that people are aware that, oh, well, it's brand new processor, oh, it should automatically be 2x. I take my job that was 1,024 ranks, I move it over here 1,024 ranks, 2x faster, great, I'm done. You know, make sure you do all of the comparisons. Why is this number bigger than this number? Well, this is per core module, and this is per node. So really, if you wanted to think the L1 bandwidth per node, you'd take this number and multiply by 16. Flops per clock, it's very similar. Per core module, it's 8. Per core, it's 8. 128 per node. Then you multiply it out. It's 128 over here. It's 128 over here. Memory latency is a little bit better over here, and some codes will see that. That's another reason why codes will speed up on Sandybridge. And then the clock rate probably changed. I don't know what the clock rate is on Rosa. Do you know? Anyone? All right, off the... Okay, so it's going from 2.1 gigahertz over here to 2.6 on Daint over here. So again, if you're completely memory bandwidth bound, that clock rate's not going to help as much, but basically it helps everything else. I mean, clock rate does help. A word about clock rate, which I don't think I explicitly call out anywhere. Take all clock rates with a grain of salt. They are, it's only like, you know, when you, I don't know how you buy a car here in Switzerland so much, but you always haggle over a price when you buy a car in the United States. And you can think that the processor is constantly haggling over a price. And sometimes they'll say that, no, this car is really valuable and it's going faster, sometimes slower. The point is that the gigahertz is constantly jumping around on you, actually underneath the covers. And you might want to try and control it, and we have tried to think if we could control it one way or another. And really, turns out that controlling it means playing around with BIOS settings, which is what we're trying to do. But as an application engineer, there's nothing you can do about it. And basically, you hope that your program runs at a gigahertz that is faster than what it actually is saying. And that is true. It is often, Sandybridge is often running at a gigahertz that's faster than 2.6 gigahertz. So there's some positives there, but you know, you don't just, you know, like that one DGEM I showed, we actually get higher than a 100% of peak. And it's because, well, given the BIOS settings and everything on that machine, it was actually going faster than 2.6 gigahertz for a substantial amount of time. So quite a bit of information on this slide, really. But I like these slides because you can see the two right next to each other. And maybe as you go and you take your application and move it over and take those numbers and, you know, you get a per rank performance improvement, and then you do another couple more calculations to get a per node performance improvement, and then you begin to wonder, well, I got 1.4 or 1.5 per node. Well, why did I get that? And this might start providing some hints. Or, you know, the next guy got 1.2, and then another guy got 2.2. You know, you refer back to this, and you might be able to make some headway in determining why that is. Any questions about this slide before I move on? Okay, so we've hinted at this. You know, you can do one hyperthread or two hyperthreads per node. And we had to, again, sort of invent a new term. Hyperthread was proprietary, so we couldn't, you have to be careful about actually using hyperthreads in our documentation and stuff. And the term thread is also overloaded. So I talk about it in terms of a single stream versus dual stream. And basically the point is that unlike most Intel clusters for high performance computing that I'm aware of, most other clusters run with hyperthreading off. We run with hyperthreading on. It's actually always on in terms of the OS. And then what really happens is the user can choose to run with one or two ranks, PEs, threads per core. And we call that, you know, running with one, we call it single stream. Running with two, we call it dual stream. Like I said, this choice is made at runtime. If you run in single stream mode, that's 1 rank per core. If you're just thinking a strict MPI only code, 1 rank per core. If you run with -J2, that's dual stream mode, or 2 ranks per core. The default is single stream. So if you don't say anything, it's single stream. I think a site could decide to change it, but I don't think you are deciding to change it. So default is single stream. And that's 1 rank per core, and that ends up with fewer ranks, 16 ranks per node, compared to Rosa. Right? Right now, we don't have any evidence that running with hyperthreads always on is a bad thing, and we're going to see that we still hope actually it's a good thing, because we can hopefully find uses for that other thread, even if we're not using it for our application directly. So now we're presented with a dilemma, but I think it's a good dilemma. Which do I run in? Do I run in dual stream, or do I run in single stream? Now, one rule of thumb that we're trying to develop, and it's more than your mileage will vary. It's your attitude about the mileage, what mileage you get will vary. So dual stream is often better if throughput is more important. And this basically says, if you look at the aggregate throughput of the machine, some codes, if they use the same number of ranks, but have twice as many ranks per node, then they will actually use half the number of nodes in dual stream compared to single stream. If they fit in memory, if that all works, in a way they will get better utilization of the hardware, potentially, not necessarily a given. Performance per node is more important. That's another way of saying throughput is more important. But it's completely plausible that if you say, I want to use, my time allocation over the next year means that I can always have a job that uses 100 nodes running. Now, how do I best utilize that node? Well, I might be more concerned about the performance per node as opposed to the performance per CPU or performance per MPI rank. And if you look at it that way and you try it both ways, maybe dual stream ends up being better. Another thing that probably goes with dual stream is your code scales extremely well. This kind of makes sense, because if your code does scale extremely well, with dual stream, you've got twice as many ranks for a given amount of hardware. So you better be able to use them, and being able to use them means your application can scale. On the flip side, single stream may be better if single job performance matters more. I want this thing done by 5 o'clock so I have my answer and I can think about it overnight. Or even like I'm starting it tonight and I want it done by the morning. That's a classic example. If a single job performance matters more, you want to go as fast as possible. Maybe single stream is the way to do that for a given number of ranks. Per core performance matters most. And another way of saying that is the code does not scale well. If you know your application scales to 1,000 cores, but it doesn't scale to 2,000 cores, and you're still waiting a long time for it to finish at 1,000 cores, well, really you want those cores to run as fast as possible. Single stream might be the way to do it. Now, the one example that I have, and the customer will remain nameless, but we had a procurement where they defined an SSP metric. And this SSP metric was a function of the speed of certain applications given a fixed number of ranks, and then how much resources did you use, and then how many resources could Cray actually deliver for a certain amount of money. And when I started off, I had a little bet with a guy that he said, we've tried hyperthreading booted on other cluster systems. Nothing seems to work. I'd be surprised if you do more than one. He gave me one. He's like, if more than one of the I don't think more than one of the 7 will run using dual stream. And in the end, For the procurement, 4 of the 7 used dual stream mode. And that was to optimize for the SSP. I mean, that's not gaming the system. That was, you set the rules, and this is what the rules tell you about how to run these codes. 4 of the 7. It was not dominant. It wasn't 6 of the 7 or anything like that. Pretty much as close to 50-50 as you can get with an odd number, right? So it was 4 of the 7. So some went one way, some went the other way. What will their users actually do? I don't know. That's TBD. Many users, they jump on and use the default and run, right? So my guess is that most users will go with single stream mode, but it is a little telling. It refers to sustained system performance, and then that's just. You have less memory per rank, yes. Yep, because you have a fixed amount of memory per node, and you're doubling the number of ranks per node, you'll have less memory per rank. Performance is the same per thread? Well, no, I mean those. When you go to dual SSP, it's all the same hardware. You don't double the number of functional units. You don't, double the memory bandwidth. So it would stand to reason that your ranks would, in terms of per rank performance, would drop by a factor of 2, right? But it doesn't always. Sometimes it drops by less than a factor of 2, in which case the per node performance actually went up. Just try it yourself. I mean, the biggest piece of advice about this is that once you have an executable and are running on Daint, it's almost trivial. I mean, I can't think, as long as you also fit in the memory, right? It's almost trivial to flip between J1 and J2. And so just try it. Try it. Get the numbers in front of you, and then make sure you kind of sit down and say, okay, how many nodes did I use for this problem? Make sure, and then decide what is your fitness function. What are you trying to optimize for? Your time allocation, or I've got a paper due on Monday, whatever, right? And then decide which one you want to run on. It might be a little bit of source of confusion, but I only can look at this as a positive because we're basically giving you a choice. Instead of forcing you one way or another, we're giving you a choice. And hopefully after a few tests, you'll settle on one of those choices, or you'll like Roberto said, you'll learn when to run one way or another, and then it will become more natural. Any other questions? Core specialization. So core specialization has been around for a few years now. And basically, the idea is to try and put all of the system noise on a core which has been specialized to only run that. And this has become more and more viable as the number of cores on a node has increased. Core specialization was non-existent when you only had one core per node, right? As you got to 2, it would take half of your resources. 4, now it's a little bit less. Well, now we're up to 16 or 32, depending on how you count it. And really, it dedicates one M number of cores or CPUs per node will be dedicated to system work. All of the system interrupts will go there, and in some cases, MPI work will go there. We'll see in a little bit. Conversely, the application will not run on the service CPUs. So the way to get that is use the app run -R option. You can do man app run, and you can read it for yourself. -R option to get core specialization. Normally on the XE with Magni cores and Interlagos, people only did R1, but we'll see in just a second. R1 is not your only choice. You can do, you can do R31. It wouldn't make much sense, but you could do it, right? You can reserve almost all the node for the system, and you know, one thing that might make sense on Sandybridge is all the numbers between 1 and 8. Why is that? Let me continue a little bit more. It starts at the highest numbered CPUs and works backwards. And the way the CPUs are numbered on Sandybridge is they're numbered 0 through 15, having 1 thread per physical core across the node. And then they wrap around and they go 16 through 31 for the hyperthreads across all those physical cores. So when we start off by saying -R1, it's going to use CPU number 31, which is the hyperthread associated with the last physical core on the last socket. If we say R2, it's going to be the hyperthread on the last 2 physical cores of the last socket. Now think about it. This is independent of the app run J1 setting. That means it will always start at the highest CPU number and work backwards, no matter what you have set for a J1 or J2. But think about that for a second, okay? If I'm running J1, which is default, I'm only using CPU 0 through 15. And 16 through 31 are just there and available. And so if I do -R1 or 2 or 8, it's going to be using hyperthreads that my application wasn't using anyway. So it seems completely viable to, if you're in J1 mode, to try R1, R2, or 3, or 4, and see if it helps you for some reason. So conversely, if you are running in dual stream mode, and you say -R1 or R2, well, that hyperthread is now going to be removed from the pool of potential places where your application can run. And so if you do R2, right, that means I can only fit 30 ranks per node. And you're going to have to take that into account when you calculate how many nodes you ask for. So again, it might be a little bit confusing at first, since we have this opportunity to run J1 or J2 single stream or dual stream. But again, I think we're pretty convinced that this is the right way to go. We're just giving you new choices. No, core specialization was possible on Interlagos. And it would, basically, you can think of course of Interlagos as always running J2. So Interlagos always used, you know, the default way on Interlagos was to use 32 ranks per node. And if you use core specialization, if you used an R1 or R2, for example, that would drop down to 30 ranks per node. So the same thing is true on Interlagos. It is available on Interlagos. It's just you have this new twist. If you're running J1 mode, you don't actually take resources away from your application. We'll hit this a couple times yet. So I think there's a man AP count that helps you, compute the total number of cores required given an app run command. I think that's what that does. I haven't played with it much. I always do it myself, but that's something to look at. So, an interesting thing, and I'm going to come in 4 slides. I'm going to come back to this. So, now we're going to talk a little bit about software, and you've seen various pictures of this before, actually already. Not exactly the same, But the point of all of this is if on the left-hand side is the XE platform, and on the right-hand side is the Cascade platform. You see that most of the boxes span both sides. And that's just to say, you know, for most things, Slurm's not on here. Slurm should be on here. But most things span. Is Slurm available on the XE? Is Slurm available on XE? You use Slurm on Rosa? Okay. So it should be on my slide. You should chastise me. No, make sure you tell my boss. But anyway, so the point is really that for most things, they're really available on both sides. Now, I mean, in all honesty, there are subtle differences that probably impact you a little bit. I think Cray is finding there are subtle differences that are impacting the user community a little bit more than we expected. One of the differences is that on the left-hand side, we had PGI GNU and Intel compilers. We also had the Cray compiler. On the right-hand side, we still have the Cray compiler. We still have GNU. And in a sense, we still had the Intel compiler. But really, the Intel compiler was new and not heavily utilized over here. And here it's default and heavily utilized. And PGI was over here, but not over there. So there's some porting. If you use PGI on Rosa, there's going to be a compiler porting effort as you decide, do you want to move to the Cray compiler, do you want to move to the Intel compiler, or even GNU? So that's one thing. Another thing is the Cray math and scientific libraries. Currently, they are, well, we say they're available on both platforms, and that is true. But currently, the Cray scientific libraries is not available to link against the Intel compiler. And again, I think we talked about this yesterday. There was a lot of people that on Rosa, they just logged on. They needed libsci, even if it wasn't the most important performance thing. They needed it. They didn't have to think about it, and it just linked. And if you moved over here with the Intel compiler, that's not quite as smooth a transition as we wanted. So some people are finding, well, I have to figure out a way to link against MKL, and that means going to that Intel website to get a link line this long, you know, just to link MKL. So we'll see how that pans out, I think, over the coming months as to whether or not we can make it smoother. But you know, coming months is not next month. And you guys are, you know, or this afternoon when you guys are getting on the system. So keep that in mind. But for most of the rest, it has been a very smooth transition. And I've had slides that I've shown over the last year. The way the Cray benchmarking worked, we first got access to a Cascade system a little over a year ago as we've brought it up. And you know, we'd had various blades. And the way that we would port codes and get them ready for the Cascade system is we would get them running on an XE system with the compiler of choice that we wanted to use on the Cascade system. And then once the Cascade was actually available, you just have to move over, recompile, and run. And the recompile should be simple because you already compiled over here. So that should be really almost no differences. And it almost always just ran. You know, if you had a successful recompile, it almost always just ran. So that was a positive experience. So in a way, even, you know, access to Daint is going to be open pretty soon. But if you're thinking about porting your code, you really should be able to get everything running on Rosa over here with the Intel compilers, even with the caveat about this libsci thing. But the Cray compiler, it goes smooth. No, not that I'm trying to get you to run on the Cray compiler or anything. So, but a lot of the things are similar between the two sides. And in particular, MPI. Okay, MPI was practically speaking, brought over wholesale, and the MPI source was just recompiled for the Intel. And then we started trying to do enhancements. But I mean, the bulk of MPI was just moved over. So in many ways, it behaves essentially the same as MPI on the XE. If you ever wanted to read a MAM page and wanted to play with the environment variables, those environment variables are all there still and all mean the same thing. Their defaults are the same in terms of eager and rendezvous, which we'll talk about more this afternoon, and stuff like that. If you were into that stuff, it's going to be there again. The two enhancements that are noteworthy on the XC so far is one, the modified MPI asynchronous progress engine threads. Okay, this is a feature that is actually available on Rosa, but there's a twist that is worth noting on Cascade. What is it first? Threads can be placed on unused Intel hyperthread cores. Well, in general, the threads can be used on unused CPUs on the node. On Rosa, you actually had to carve out an unused CPU by doing core specialization. But on Cascade, they will automatically use the hyperthread cores if you're in J1 mode, if you're in single stream mode. Remember, single stream mode, you're only using half of the hyperthreads. So this was designed to automatically use the other half just by sending the environment variable. I have another slide on it in just a second. So this is going to be good. And I guess even deeper, what is this? You know, if you do I send and I receive, and then you have some amount of computation and then await all, the idea with that is often I want to make forward progress. I want the communication to happen while I'm doing computation. And, you know, people often think, oh, I've done everything necessary, but it turns out that the MPI software stack underneath is quite a bit more complex. And given that, plus the timing of various things, it's not a guarantee that that overlap will happen. You need something to be kind of actively monitoring the situation. That's called a progress engine. And this is exactly that. This is a place where to put that progress engine so it can actively look for messages coming in or ready to move. So it basically helps with your overlapping communication and computation. Now, not all codes are set up to use overlapping communication and computation, and some codes, even if they were already set up to do it, they were already getting a benefit. So it's not a guarantee that this will help, but it's another tool in the toolbox. XC hardware collective engine is another thing. We have hardware support for barrier and some all-reduced collectives. You can plan to use these using this environment variable, but you must also link against libdmap. And dmap is a particular low-level communication library. You know, this is an interesting one. It's touted as being great. It does have fast barriers implemented in hardware. I will also admit, as an application engineer, most of the time, if I see barrier taking a long time, the first place I look is some kind of load imbalance, either in the code or even induced by something. And there's lots of things that can induce load imbalance. OS noise, which we're constantly trying to minimize, or even just a near socket versus far socket. So if you have barrier or all reduced taking a long time, this might be something to try, but you know, keep in mind that if you try this and you don't run faster, think to yourself, okay, is there some kind of load imbalance for some reason? Yeah. You know, hardly anyone tries to use it. Do you try and use it?
I have tried on the XE, and it's slower than two-sided communication. I'm wondering whether we should try again on
I don't know of a lot of specific tests, but given everything I said about things moving over wholesale, and the hardware is similar enough in those regards that I don't expect magic to happen. You know, the hardware is faster in terms of lower latency and better bandwidth, but is there something in either the hardware or software that magically accelerates MPI one-sided? And I can't. Well, this is to enhance those collectives, and I've already let the cat out of the bag that we're also putting in DMAP to improve the all-to-all performance. That's not quite available yet, but it's coming. But really, you know, I would say if you want to do one-sided, I would seriously consider, you know, going whole hog and trying one of the PCAS languages, Cray, Fortran, Schmem, type of thing. And those rock on this machine. They did pretty well on Gemini, but they're even. That's good. Okay, any other questions? No. Oh, for the all-to-reduce collective? Yes, this accelerates the hardware. Oh, I should point that out. Yeah, the hardware acceleration is for a limited number, right? And I can't immediately remember if it's one double or two doubles, but it's not four doubles. I'm pretty sure on that one, right? So if you're doing an all-reduce where you're all-reducing a megabyte, you're not using the hardware acceleration. And that sort of makes sense. Hardware acceleration literally means you're doing the operations in the areas, and it has only memory for a couple of words. So yes, this is meant to, you know, this is meant to try to speed up barriers where you're basically passing around a 64-bit integer and some of the floating point collectives where you're doing one or two words and basically it's acting like a barrier, but not larger than that. I know people inside of Cray have played around with it. Do I think this is majority? No, nowhere near the majority have used this. You know, the default is to not set the environment variable. Well, yeah, no one uses not a minority of people use DMAP as part of their MPI today because the default is to not use it, and most people don't see a benefit of this. Either barriers are not a major component, or even if they are a major component, it's not. This doesn't help. It will be interesting to see how this changes when all-to-all starts using DMAP. That's the optimization that's coming. Is all-to-all is going to use DMAP, and then I mean that doesn't apply just to single word all-to-alls. That applies to any size all-to-all. So we'll see if it. I almost guarantee it will become more common. I don't know that it'll turn into a majority or anything like that. But one last word about linking in DMAP with your MPI, and this is true on Rosa, is if you link in DMAP, you are kind of saying, I'm going to give up some MPI capabilities to get other capabilities. And the one MPI capability that I know you give up is multiple binary launch. Most people don't do multiple binary launch, so most people don't care about that, but an MPI purist would. You know, they say, oh, why can't you implement this? But anyway, so that's, you can't, if you link in DMAP with your MPI, you can't do multiple multiple binary launch anymore. So more about this async progress engine. You know, this is to improve communication overhead. Starts a helper thread, and then you have to say, where is that helper thread going to run? That helper thread runs the progress MPI engine while the application computes. This is only applicable to messages that use the rendezvous path. We'll talk about what that means this afternoon, but it means it's got to be a substantial size. We're not talking single word. I think this is at least, might be at least a couple kbytes or something like that. If it's smaller than a couple kbytes, it uses a different method, and overlap happens sort of anyway. So it only happens for some message sizes. To enable it, these are the environment variables that you set. When using one stream per core, you set this environment variable, you set thread safety, and then you enable it. And then you can just run it without anything else on the line. Because remember, in single stream mode, the other hyperthreads are there anyway, and it's been designed to use those hyperthreads. When you're running with 2 streams per core, then you still have to set these environment variables. You don't set this unassigned CPU thing, but you do now have to do -R. And again, you can do 1 or 2. If you start doing more than 2, well, these things are taking resources away from your application, so you're probably not going to do more than 2. And we have seen 10% improvements with some applications. Milk is one application. That's a QCD application from that's used in the United States quite a bit. I don't know if it's used in Europe as much, but QCD application, it runs best in single stream mode, and we also tried it with this async thing, and it got another 5% boost with this async thing. So my hyperthreading optimization chart then, or this is almost in a way a high-level optimization start. You're going to start in the upper left-hand box, really. When you jump on the system, the default is single-stream mode, and there is no MPI async. You're going to collect a performance baseline here, and single-stream mode, remember, in a way, this is kind of maximizing per CPU performance, maximizing per rank performance, if you want to think that way. There is little to no MPI communication overlap. Little to no is really a fuzzy thing here because it really depends on your app as to whether or not you're already getting async. I'm not saying it doesn't happen. I'm saying it's kind of harder to happen in this mode, right? But this is default. This is where you're going to start to run. One thing you might try next then, because it might be pretty easy to do, is just to try single stream mode with MPI async on. Again, you're trying to maximize single CPU performance, but you're hoping that turning async on will improve communication performance. It does overall performance improve. It's not a guarantee that it will improve. It's not a guarantee that it won't slow down. Turning on those environment variables does add overhead to the MPI library, and if your code was already running efficiently, already getting lucky and having overlap, or if it didn't have, couldn't take advantage of the overlap anyway, and then you added the overhead, there's a chance it slows down. That's why it's not default. So basically run it and see if it helps or see if it slows down. But it's a pretty easy thing to do. Now you can also move in the other dimension, and that's try dual stream mode without MPI async. This is without core specialization or anything like that. And we're basically trying to see, well, how does our compute behave? We're optimizing perhaps per node performance, like I said before, or maximizing performance by using many PEs, however you want to look at it. And then is it better? And I stress better in quotes because you have to decide what better means in this case. Time to solution or conservation of my time allocation. Whatever you want to say is better. You have to do that. And again, it can be using twice as many ranks on a given number of nodes, or it can be using half the number of nodes for a given number of ranks. There's a couple of different ways to look at it. Now, once you have these 3 runs, maybe if this was successful, and maybe if this was successful, you ask, what's the combination? And that would be dual stream mode with async. The goals are optimizing per node performance or maximizing APU and improve communication performance. But remember, I have to give up 1 or 2 hyperthreads to do this. And so again, you have to ask yourself, is this better? You know, it's not a guarantee that if this is faster and this is faster, this would be faster. And you have to give up a little bit of resources, so you kind of have to take a tiny step back, and then you're going to see if there's a step forward. But that's kind of how I imagine these things try. We've had the benchmarking group so far has absolutely tried this. A few of us have tried this. I think it's relatively rare that we end up here. But that doesn't, this stuff is also pretty new to us. So I think that might just be, you know, we haven't had the time to try it yet, and we ourselves might be leaving some performance on the table. Any questions about this one? Okay. Running OpenMP and the Intel PE. Okay. Intel hit on this a little bit. I'm gonna pick on Intel a little bit here, because really, in my view, there's a problem with the way Intel implements OpenMP. And while they don't really come out and say it, what actually happens is the Intel OpenMP implementation, the first time you hit an OpenMP region, it creates a helper thread. It says, here's a helper thread. And then Intel just seems to think that the operating system is supposed to know, oh, you know, fake out. Sorry, this thread isn't supposed to do anything. I'm going to create another n number of threads that are actually your application threads. And that helper thread, just try and forget about it. Well, this is a problem on the Cray thing, on the Cray, because Cray's default is to bind threads to CPUs as you go. And if you said on the app run line, we have this -d option that, generally speaking, is the same as the number of OpenMP threads. -d4 is going to reserve 4 CPUs for you to run on OpenMP. OpenMP num threads is equal to 4. All great, lines up on the Cray compiler when using the Cray programming environment. On the Intel programming environment, it actually turns out that, oh, I don't have 4 threads, I have 5. And one of them wraps around, and it turns out the wrong one wraps around and causes problem. So, and it's not difficult to imagine, you know, doubling up user threads on one core is just going to be bad for that core performance. So the workaround for this issue is basically to shut CPU binding off. And this allows user compute threads to spread out. The operating system really does kind of forget about this helper thread, and your user threads spread out across the cores. And so ideally, the helper thread no longer impacts performance. Again, I stress this is only an issue when running OpenMP programs that were compiled and linked with the Intel compiler. If you're using Intel and not using OpenMP, you don't care about it. If you're not using Intel and using OpenMP, you don't care about it. It's not an issue for GNU or Cray. So the way we do that is a little bit tricky. So when running with a depth, and this is the -d option, when running with depth divides evenly into the number of CPUs on a socket, which is what I recommend, right? There's 8 or 16, depending on single stream or dual stream, on a socket. If it divides evenly into that, then your app run command, your OpenMP environment variable is going to be something. You can actually say less than or equal to depth. I don't care if you can spread out. Your depth can be wider than the number of OpenMP threads. But on your app run line, depth is some number, and you'll be able to number of sockets times the number of functional units, and you say, you're going to run one process per integer functional unit on Interlagos. This would fit 32 at default. I'm almost certain that's the way it's set up on Rosa, right? And for Sandybridge, if you multiply the number of cores times the default number of threads per core times the number of sockets, you end up with 16. So there, on the Sandybridge side, at default, you're going to be running 16 ranks per node with the choice of going to 32. Got it? I'm willing to pause here for a minute because it's the source of quite a bit of confusion sometimes inside of Cray as well. So continuing on, the core module, this bulldozer module on Interlagos, had 2 AVX vector functional units. Each was 128 bits wide. And what they would do is they would take the AVX instruction and actually, under the covers, split it up into 2 128s and then feed it to the vector functional unit. On the other hand, Sandybridge has 1 AVX functional unit, and that is 256 bits wide, and they don't break it up. So on Interlagos, you could still compile SSE vectors that were only 128-bit wide and get potentially pretty good performance. It's less clear that that's the case over on Sandybridge. On Sandybridge, if you're going to vectorize, you might as well go whole hog and vectorize AVX and get the 256. So Sandybridge, in short, is even more AVX. I mean, it's more a pure AVX thing. You know, strongly recommended to compile with that XAVX when possible. Another difference on the left-hand side, Interlagos had 1 fused multiply add functional unit. So fused multiply add, it really began to break down because Interlagos, they have that their code name was a bulldozer module, and that bulldozer module actually has 2 integer units but shares a floating point unit. And people stop really saying, well, what's a core? You know, depending on who you would talk to, they would say, what is a core? What is not a core? And so we came up with the term, well, core module refers to this bulldozer module with 2 unique integer functional units and a shared floating point unit, a shared vector unit. On Sandybridge, you can basically think, well, that's a core, because everyone in the Intel world still calls it a core with 2 hyperthreads. So we're kind of going back to the term core because that's what everyone wants to talk about in Intel land. So you can think of a core module. If you want to briefly think about Interlagos and then move on, you can think about a core module as being similar to a core on Sandybridge. So let me go to the next line. Like I said, the core module has 2 integer functional units. Each integer functional unit is capable and basically runs its own process thread, right? And the default way of running on Interlagos is to, in fact, pact a 1 process thread, 1 rank on each one of those integer functional units. On Sandybridge, like Intel hinted at two days ago, the default way of doing it in all of HPCC is to run just 1 process thread per core. And that's why everyone calls it a core. But we have the capability of running either 1 or 2 user threads at runtime. So all total, if you multiply everything out, the number of core modules times the isn't so important, as there was 1 connection connecting into a single die. A single die of a single socket. The node was 2 sockets. Each socket had direct attached memory, but inside those sockets, each had 2 unique die. So from a programmer's point of view, really, I would say that this wasn't a two-socket. Don't think of it as a two-socket system. Think of it as a 4-die node with an interconnect between those 4 die. At a high level, we'll see this is relatively similar to the XC compute blade with Intel inside. We have 2 sockets. Each has direct connections to memory, and there is one of the sockets attached to the network. So in that sense, they're similar, right? Both have 2 sockets. Both have one of the sockets attached to the network. Both of the sockets have direct attached memory. The thing that's different is on Intel now, instead of having 2 die internally, we really have one monolithic die. So before, we had each die had a total of 4 bulldozer units. And each bulldozer unit, they had their own interesting definition of what was a compute CPU and what was a compute module and stuff like that. But they had 4 bulldozer units for a total of 8 threads on here. Here we have 8 cores in this socket. And each core is capable of having running 1 or 2 hyperthreads. So we're not going to, if we're thinking about shared memory programming, on Rosa, I would have recommended don't go beyond a die, and a die was 4 bulldozer units, right? 4 bulldozer modules. Again, I would probably recommend for OpenMP or shared memory programming on the Cascade, don't go beyond a die, but the die is now 8 cores total, each with hyperthreads or not. So similar, but a little bit different. Now we're going to go into a pretty dense slide, but we'll step through this little by little. And I made it dense. I wanted everything on one slide for a reason, and you'll get PDF versions or already have PDF versions of this, and you'll be able to reference it a little bit. So on the left-hand side, we have Interlagos. On the right-hand side, we have Sandybridge. And we'll just walk down each bullet point. So on the left-hand side, Interlagos had 8 core modules, is the term that we came up with, per socket. But those core modules were split between and had 4 core modules per die. Right-hand side, Sandybridge, 8 cores per die. And there's only 1 die per socket, right? Next one, 4 die per node, because we have 2 sockets, 2 dies per socket. On Interlagos, only 2 die per node. Again, this is repeating what I just said. Fewer die means fewer NUMA nodes is a term that people use fairly often as well. Core, yeah, so we've had Cray over the last almost decade has had real problems with terminology. And that's because everyone a decade ago knew a CPU was a processor, was a core, was a socket, right? But as we've progressed into the multi-core era, Cray has had to, since we write contracts on this stuff, we've had to try and be precise and add terminology. It worked out pretty well when they started putting multiple cores on a processor, because then we would say, oh, okay, a processor is maybe a socket, and you would have multiple cores in there. It began to break down when they put multiple dies in the socket, and with Interlagos. So this is the XC to XE comparison and early performance tips. I'm guessing that maybe not all of you, but at least some of you have been working on Rosa. So I'm going to compare and contrast, and I have a processor bake-off kind of that we'll step through. Pretty dense slide, but hopefully you also it'll be a good slide to reference, and you can tell when you are are running at different speed and why. So the basic outline, only these topics that we have to do. So the node is similar but different. You'll see what I mean there. You have the choice of hyper-threading. Like I said, Intel was a little surprised yesterday when they, or a couple days ago when I asked them, well, what are you going to say about hyper-threading? And they're like, oh, HPC doesn't use hyper-threading. Well, guess what? Now they do. So core specialization, it has been around, continues to be around, but there are twists to this. So we're going to go over that. Software environment is similar but different. I'm going to point out a couple of MPI enhancements already now, because most of MPI is similar, but there are some that are couple that are new and important, I think, to this environment. So we're going to touch that here. Hyper-threading. Then we're going to take that and develop a hyper-threading optimization chart. Talk a little bit more about Intel OpenMP, network sustained bandwidth, brush up on your I/O, and then if we have time, I even have a 3D FFT story that was something that we did, learned on the XE, but probably is still applicable. So we'll see how far we get through all of this. So first thing, this is an Interlagos compute node. Interlagos is AMD, this is Rosa, right? But I wanted to refamiliarize yourself with that, so then we're going to move forward. The things to remember about Interlagos is that you had a connection to the internet through their HT link. All right, the fact that it's HT